Suppose we start with a given curve representing a function, as we have here. And then we just say we're going to break this interval between a and b into a set of subintervals. And we'll say that they're going to be of equal size, so we can call that maybe delta x. And then we're going to construct some rectangles. And those rectangles are going to be covering each of the intervals, and the rectangle will rise to meet the curve at some value inside the interval. So in this case, it's meeting the curve, let's say about 3/10 the way inside each of these intervals. And then when we add together the areas of those rectangles, we can get an estimate of the area under the curve. We're also going to say that when those curves go below the x-axis, that we're going to call the area a negative value. And so what we're doing is we're taking the width of each interval and multiplying it by the value of the function at a specific point inside that interval. And then when we add all that together, that's what we're calling the integral. This sum of squares here we call the Riemann sum for f on the interval from a to b. Now obviously we can get a more precise estimate of that area as the intervals get narrower and narrower, and we can also improve on the use of squares by substituting trapezoids, which will give us a more precise estimate as well. So if our function f is continuous on the interval from a to b, and the interval is partitioned into n intervals of length delta x, each of which is b minus a over n, then the definite integral of f over interval ab is given by the limit as n approaches infinity of the Riemann sum, where again c sub k represents some value inside the interval that we choose to set as the value or the height of that particular rectangle. So here we say the x value of this point right here would be c sub k, and the y value would be f of c sub k. And in this case, k would be equal to 1, k would be equal to 2, 3, 4, 5, 6, etc. And as we say, we're going to break it into larger and larger intervals. The limit of that is what we define as the definite integral over of function f over the interval from a to b. The notation we'll use then for that limit is here. We have the integral from lower limit a to upper limit b of f of x dx. And we read that as the integral of f of x dx from a to b. This is the definition of the definite integral. So the symbol that we're using here, if we take a look at the different pieces of it, we have the integrand, which is the function that we're integrating. We have the integral sign. We have the lower limit of the integration. We have the upper limit of the integration. We have x as the variable of integration. And then when we have found the value of this integral from a to b, we have evaluated the integral. Okay, and that's basically the definition of the definite integral, which we can represent as a number because it's the area between the axis, x-axis, and the curve over the interval from a to b. And in this case, that is an area of 5.64. So our estimates before this were pretty good because we got to about 5.66 as our most precise estimate.